Okay, today we have Brandon Shapiro talking to us about higher categories via familial functors via polynomials. Welcome.
Great. Thank you so much for having me. I'm really happy to be here this week. And my title pretty much tells you the outline of the talk. I'm going to say a little bit about higher categories and sort of what I'm interested in doing with them, and then talk about how familial functors, what they are and how they relate, and then get into why I started thinking about polynomials, which I think was a little bit different from a lot of other people. So first of all, what do I mean by higher categories? So, which I will henceforth refer to as higher cats. And so maybe the lions of the higher cats might be the ones that look kind of like this. Two categories where we have the usual objects and morphisms that we're familiar with from one category, but we also have these two cells, which look like this. They go between arrows, which have the same source and target object, and they can compose horizontally and vertically. And I'll say a little more about that later. Then we also have a different kind of higher category, double categories, where we still have objects, but we also have two different kinds of morphisms, which I personally have gotten used to drawing as the ones with the tail at the end and the ones with the circle at the end. These are also sometimes called horizontal and vertical morphisms, though some situations you have to draw them in different directions. And then we have squares. So instead of two-dimensional cell shapes that look like these flat lemon things, these ones look like squares, and they go between the two different kinds of maps. We could also think about multi-categories, which don't have any higher dimensional cells in the sense that we see over here, but instead have very different kinds of cells in that we have n-to-1 cell arrows for any n. And so that includes these 2-to-1 and 3-to-1 arrows I've drawn here. You could also just as well have 1-to-1 arrows, like in categories, or even 0-to-1 arrows, which you want to think of as constants. And we have composition of these things too. If we had a diagram like this and we wanted to compose it, any tree of this form, this would compose into a 1, 2, that's 0, 3, 4-to-1 arrow in a multi-category. But today, an example that I'm going to use a few times to describe some of these things is just ordinary categories. Those are a perfectly good kind of higher category as well. In fact, in many ways, they're one of the best. So what do I actually want to do with these? So I'll tell you my goal, which is to generalize the features of category theory. The things that we're used to doing, being able to do for categories, and do it in a way that works for all of these different kinds of higher categories. So we're generalizing features of category theory to any type of higher category. And so what are some things that I might want to generalize? Well, ordinary categories have nerves, and these were generalized by Mark Weber. Another thing that we can do for ordinary categories is enrichment. And this is the subject of the second paper that's going to go into my thesis. And so I won't talk too much about nerves, which are sort of about taking these algebraic structures of higher categories and representing them in a more combinatorial way, which can be convenient in various ways. Enrichment of categories describes when we want the morphisms in our category. So instead of a set of morphisms between two fixed objects, we want to replace that with, say, an abelian group of morphisms, or a space of morphisms, or maybe even a category. And we often want to do that for these other kinds of higher categories as well, where maybe the top dimensional cells, like the squares in a double category, we want them to form some more complicated structure. Is there a question?
Are you going to kind of do the same for polycategories too, or just multi-categories?
Yeah, polycategories work just as well. Two categories, so these are just examples, but yeah, polycategories work fine. Different versions of polycategories where you can like glue along multiple different vertices, that's fine. Monoidal categories of most types. From the ones I've seen, I think everything except strictly symmetric monoidal categories you can model in the way I'm going to describe. So yeah, it's fairly robust. Not all of them, sorry?
Just saying excellent, thank you.
Oh, great. Yeah, not all of them can necessarily be enriched. Well, all of those ones can be enriched. Yeah, there are some fairly non-restrictive conditions. And then in perhaps future work, some other features we might want are things like limits, maybe some theory of fibrations, or my dream, the neonatal lemma, and embedding, and general stuff. So this is what I started this project wanting to do. And I'm not going to tell you too much about how any of these things work today, or in fact, anything more than what I've already said. But one of the harder questions to answer before being able to do that is sort of relating to what Valeria just asked. What is a type of higher category? What does that mean? And so that's what I'm going to talk about today.
Can you say why, like, you would tackle enrichment before some of this other stuff?
Yeah, so part of it was that it was kind of just one of the things that I had thought about the most thoroughly. Because it got into, like, I kind of went about it backwards. So I started with thinking about what a type of higher category was, which I'll talk more about in a minute. But then I went straight into, okay, well, how can we, like, what can these features do? How can we combine these in different ways, like enrichment or internalization? I was also interested in things from homotopy theory, where you have sort of like iterated enrichment ad infinitum. I wanted to be able to talk about that, and so I was really thinking about how you compare these things. And enrichment proved to be a really interesting space for that. And so I wanted to, for instance, show how normally categories enriched in categories give you two categories. And so I wanted to create like a more general formulation of that statement, where one higher category enriched in another gives you a new one. And then I kind of backtracked from there to, okay, well, what does it actually mean to enrich a higher category in something more general? So it kind of just happened. But also, there are other motivations from homotopy theory as well, because I was interested in the interaction between enrichment and nerves, which also sort of generalizes a nice picture from globular categories. Yeah. Happy to talk about that more later. Yeah. Any other questions? Cool. Plenty of more time for them if they come up. So I'm going to tell you sort of piece by piece what I mean by a type of higher category. So I'm going to call it a higher category schema. And I chose this word intentionally because I think it is a good description in the sense that I'm giving you a schematic notion of what a type of higher category is, an instance of that schema in the way the database theorists might talk about it, is going to be a higher category of that type. And so I'll say more about that soon. So what does this information consist of? Oh, and one more thing, because I know that people here have worked on categorical database theory. I'm not using schema in the same sense of, say, David and others' papers on modeling databases as functors from a category. I will say something about that, but these schema are different. And there is a way of connecting it to database theory, but it's not quite that one.
Schema, like the algebraic geometry schemes?
No.
Okay, just checking. I didn't think so, but you know.
Yeah. I don't think it has anything to do with that. If you believe in database schema being finite limit sketches, that one is the most appropriate. But we're not going to see that. That actually connects up to how you define nerves in an interesting way. But these ones will be presented differently. So the first thing we need is a category which I'm going to call C. And sometimes my curly C's look like E's, so I'll try to distinguish that. And we're going to think of C as a category of cell shapes. And so I'm going to tell you what C is for some of these. So this is part of why ordinary categories are a great example to start with. What are the cell shapes? Well, the cells are all either vertices or arrows. And so I'm going to say that a vertex is a 0 cell. And an arrow is a 1 cell. And the morphisms in this category are going to be inclusions between the cells. And so the vertex includes into the arrow as its source and its target. And then if we look over here, for two categories, we also have source and target 0 cells in our 1 cells, and then in addition we have some 2 cells as well. And these have source and target 1 cells. And there are some equations between these maps that I'm not going to draw because we won't get into it. But those are what ensures that each 2 cell has a single source and target object.
When you say inclusions, you mean anything more precise than arrow, like monomorphism or something like that? Or
in practice, we often want more conditions like that. You might want that this is a direct category, so all the arrows kind of point upward in dimension in some sense. You might want them to be monomorphisms. We don't need any of that today. Some of these things might. Nerves don't need anything else. Enrichment needs something. Enrichment needs you to look like a direct category at the top. Other things may need more. But yeah, that's a common feature, but it's not always necessary. And so what do we do with these cell shapes? We say that the underlying cells of one of our higher categories these are going to assemble into what various people call a functor, or a presheaf, or a diagram. I'm going to model it as a functor from C op into set. I'm often going to call these diagrams. And so the way to think about this is that over here, each of these arrangements of cells is one of these diagrams. And I'll say more in a second about other ways that we can think about them. But here we have, this is a diagram of vertices and arrows. We have a set of vertices and a set of arrows. And so in particular, for two categories, if we have a two category, or rather just the underlying cell data of a two category, it looks like this. I'll give them names, A, B, C, F, G, H, K, alpha and beta. So one way we could see this is as a diagram of sets. Of this form. X2 is the set of two cells, alpha and beta. X1 is the set of one cells, and X0 is the set of objects. And the maps go the other way, because each arrow has a source and a target object. It's a convention, writing the arrows in this direction for the cell shapes. I choose it because it's common in homotopy theory, where I spend a lot of my time, and also it works nicely for things like the Ineta embedding. Another way we can think about this is in terms of databases. And now this is using the categorical formalism for databases that David has written about. So one way we might write this is as data tables. So X0 is a table where all we need to show is the names of the objects. Those are A, B, and C. X1 is going to carry a bit more information, where our morphisms are going to have a name, a source, and a target. And so we have F, G, H, K, and we can write in the objects that they go between. And then we can do something similar for X2, where we need their name, we need their source and their target. And so we can represent this underlying cell information as a database, which perhaps could be useful for some computational work on higher categories. That would be neat. Also worth noting that we can do this kind of efficiently by not keeping track of the source and target objects of the two cells. So the database makes it a more efficient representation in terms of databases. And a lot of the rest of what we do to describe higher categories can be phrased in a sort of database-friendly way. And then just to establish some notation, I'm going to write C hat for the category of functors from C-op, or diagrams. And I may use the Oneta embedding, which I'll write as Y, which just sends each cell shape to the diagram with a single cell. So what else do we need to define a higher category schema? Well, we also need some algebraic structure. And so what does that look like? So to describe the algebraic structure, we need a functor from C hat to C hat, which is of the following form, at least up to isomorphism. So if we have C, an object in our cell shape category, so that's a particular cell shape, and X is a diagram over C, then this functor, which I'm going to call T, needs to have the property that Tx of C is a disjoint union indexed by some set SC of representables, represented by some diagram ET. And in order for this to form an actual diagram over C, it needs to be functorial in the sense that...
E sub t?
Huh?
Is it like E sub t? E of t somehow?
I write E of t, or just say
E of
ET.
t, okay.
Yeah. So for both of S and E are going to be functors. So S is going to be a functor from C op into set, and E is going to be a functor from the category of elements of S into C hat. Now this may seem kind of out of nowhere. So where does this come from? So for C, the cell shapes that we use for categories, then X, think of as X0, X1. This is just a graph in the category theorist sense, namely a diagram between sets like this. Then we have the free category monad, T, defined as follows. So the vertices of Tx are just x0, and the arrows in Tx are given by paths in X. So these are finite directed paths. But in fact, we can rewrite this. Vertices in X are the same thing as maps of graphs from the walking vertex, which I'll just write as a dot, into X. And paths, we can break up according to their length. So we can think of this as a disjoint union of paths of length n for all n. And so then we can write it in this way as a disjoint union of representables, where the representing path is the sort of walking length n path, which has n adjacent arrows. And a map from that into X is just a length n path in X. And so these describe the composition operations we have in a category. So in this case, so here we have that S0 is just the point. S1 is the natural numbers. So I'm actually going to rewrite this operation as 0. So then we can say all at once that En is this length n path. And when n equals 0, that's just a point. These are all the operations that go into the theory of categories. And so we then have that category is an algebra so we have a structure map from Tx to X, which says that for any arrow in here, which is in fact a string of arrows, we can compose it into an arrow in here. And so this S is the operations outputting a C cell. And ET is the arity of an operation.
So from a database point of view, what we're saying is that each of these Tx of C's is a disjoint union of conjunctive queries, which is
Exactly.
a very nice thing. So
Yeah, and for like, for one of these operations, so if we take the operation that sends this diagram to a single arrow, we can write x in database language, and forgive me if I butcher SQL, as x1 joined with a copy of x1 on the condition that the target of the first arrow equals the source of the second arrow. And so this database analogy goes pretty far. And then we just say we need a map from that table into our x1. So this is a lot of what you need to define a higher category theory. We have all of these operations. We know how to we want to know how to compose them into a cell. And so over here we would see that like an arrangement of cells like this should compose into a two-cell, because we can compose them vertically, we can compose them horizontally. And so the operations include larger ones like this. Or here, we can compose squares vertically or horizontally. And there's a unique operation of that sort which encodes associativity. But there's more, but encoding associativity is a little bit more complicated. And as we can see just in this example that our unit x into tx, informally we can describe it as the fact that for any edge in x, we can also regard that as a path in x, which is an edge in tx. And similarly for multiplication, if we have a path of paths, which might look something like this, where the inner paths are in parentheses, and this is like a path of them, you could also do sort of the opposite way of composing three arrows like that. These are going to go to just ordinary paths, namely the one where we forget the parentheses and have three arrows. And there's only one choice of this in Tx. We only have a single operation for composing three arrows. And so this encodes associativity. And so, sort of going back out to this definition of a higher category schema that I still haven't completed, we also need Cartesian natural transformations of the form from the identity to T and mu from T composed with T to T, which make T a monad. And I'm not going to talk too much about why these have to be Cartesian, but the point of it is that up here we see that this diagram is actually the same as this one, as the ones here, when we ignore the parentheses. That's very vague, but the point of it is that equations between different composites of operations in a higher category, like these two here, should be between operations which are taking in the same diagram.
What was the part where you said there's only one path of length 3? What's that part?
Yeah, so in our operations for categories, our operations for arrows are indexed by natural numbers, and each natural number gives you an operation with the arity, the string of n arrows. So we can compose one arrow, a length 0 path with an object into an arrow. We can compose a length 2 path into an arrow. That's the usual composition. We can compose a length 3 path into an arrow. That is its own operation, and there is only one operation which has that arity. Only one operation sending a length 3 path to an arrow. And so what this version of associativity says, any nested operation, like the ones that I've drawn here, has to be sent to an actual operation that we've encoded.
Yeah, and T is the encoder of operations.
Yeah, so this is a particular choice of T.
Okay, got it.
And there's only one choice, which is a sort of quick way of saying there's associative. There's only one possible choice that has the right arity.
But Brendan, it's obvious that you ought to be monoidal, right? So the Cartesianness is where it's this uniqueness that you're kind of mentioning now that gives you the Cartesianness, I suppose. But I mean, not seeing very much where it's coming from quite yet. I mean, I understand why you want it, because you want associativity to be a thing that is unique. But I don't know exactly where that structure is coming from.
Yeah, so maybe I've been a bit unclear about that. Cartesianness is not giving us associativity. What Cartesianness does is says that what Cartesianness says is the following. So what Cartesianness says is that if we have some nested diagram, maybe it's even longer, like this, where we have a path of paths, we need this to correspond to a proper operation, to one of the operations that we've described. So this needs to give us some t in S1. What Cartesianness does, Cartesianness imposes the property that this thing has to be isomorphic to the arity of that t. That if we need an operation that can send something like this, a nested path of this form, to a single arrow, then we need that operation to take in the same sort of underlying cell information where we forgot the nesting. So in this case, it would be 5 arrows. That operation may not be unique. So for instance, if you are talking about bicategories, then, so indicate this is clearly separate. If we were doing this for bicategories, then our list of operations, which we can compose into a one cell, might include, okay, we still have the point, we still have a single arrow, we still have a pair of arrows, but now there are different ways of composing three arrows in a bicategory into a single arrow. Those aren't always the same, but nonetheless, if we took some nested operations in here, which is going to be a terrible mess to draw, but if we did that, we would still want the sort of unwound operation that we get from them to have the same underlying cell data. Does that answer your question?
It does give me some understanding. I mean, you see, what I was trying to say is that I understand that to have a monoidal structure there, because any composition will give you monoidal stuff. But I think now I understand from this big bicategories example that, you know, we are trying to glue things kind of as much as they will be glued by the other structure, right?
Yeah.
The structure of the bicategory does not force these two compositions to be the same. So you want to keep that level.
Yes.
So, you know, what I was kind of worried about was the fact that I thought monoidal structure, yes, but Cartesian structure requires an universality of the monoidal structure. And I wasn't seeing where the universality was coming from. But I think I now have at least some sort of motivation in terms of this business that we want to make things as equal as we can, but not more than we can, right? So.
Yeah, definitely. And I admit it's a very fair question because I'm being kind of intentionally vague about what something like this actually means for the sake of time. But I will just say quickly to give some contrast, if we didn't have Cartesianness, something that you might be able to do is say, if we had an operation which was meant to describe inverses, so if this were f, this were meant to be f inverse. And so we wanted to encode the equation that the composite of f and f inverse, normally we want that to equal the identity, except the identity is just a point. And so we're trying to compare two things which have different input information. One of them involves like an arrow, as well as sort of its formal inverse that I've added. The other one is just a point. This is not something we can do in a Cartesian setting. And whether or not we want to include that or not is debatable, but we're going to get stronger results if we don't. And so that's sort of the approach that I've taken.
But there is a monad that can do that.
Yeah, I mean, there's a free groupoid monad on graphs.
And it's polynomial.
It's not Cartesian.
No, but
I believe it is familial, which maybe I haven't written down yet, but that's
that's type 2, right?
Yeah. So maybe I should write down now. That a higher category of type T, where I will abuse notation significantly by calling this whole thing T, is an algebra for this monad. For algebra for so we call this T a familial monad. And familial is short for familially representable because we see that it's given by not a representable, but a family of representables, where that family can vary based on C. And so this is what I mean by a type of higher category. But, and so this is a monad on diagrams over C. But you may be thinking that, what are we supposed to do with that? I've given you a category of diagrams. I've told you that a type of higher category is a certain kind of monad on those diagrams. This is all a lot of information to keep track of. Much more than like somebody trying to generalize interesting constructions and such is going to want to deal with. We want there to be a more combinatorial description of this information. And this gets into the monoidal structure that I think Valeria was mentioning earlier, and that I've sort of very vaguely hinted at in these pictures here. I didn't actually write what eta and mu were in terms of these disjoint unions of representables. It'd be kind of messy. What I did instead was said, okay, well, we need edges to go to paths. We need paths of paths to go to paths. We need to be able to choose operations corresponding to these things. So I'm going to give these letters. And I hope you'll forgive me for using a lowercase e for one of them, given how I'm writing categories. But it seems like the right choice based on eta and mu. And so then I can write down a theorem. Maybe I'll do it up here. So my main theorem for this talk is that we don't have to do it as a monad, because familial monads on diagrams over C can be completely described, and by this I mean an equivalence of categories, though I won't get too much into what the categories are. These can be completely described by tuples of S and E. So S is a functor from C op to set. E is a functor from the category of elements to diagrams over C. These describe the operations and arities. But then we also need them to include the original cells and to include composites of operations. And so I'm going to write E and M as well. And this is much without necessarily telling you how we express those for the sake of time. And this is, are people having a hard time seeing?
No, I'm pretty stuck.
Oh, okay. And this is much more straightforward data. And so why do we want something like this in practice? To me, there are several reasons. The main two are that it's a much more convenient language for describing these generalized constructions from category theory. It's much easier to say, okay, we can tell you what enrichment means in terms of, by saying, you know, for all t and SC, we have some operation indexed by ET. And we can tell you what E and M.
Sorry, maybe I missed it. What are E and M again?
So E and M are my labels for these vague constructions over here, where...
So not the same as eta and mu or something?
So eta and mu have precise meanings as natural transformations from here to here. I'm saying that E and M are something else given just in terms of these operations and their arities.
Okay.
I'm happy to talk more about what those are,
Okay.
but
So
it gets very technical. Yeah, so this was some intentional vagary, for which I apologize. Yeah, so this is a more convenient language. Talking about operations and arities is, I think, more appropriate for doing higher category theory, where that's really how we think of it. What kinds of diagrams can we compose? And what equations do we have between them, which, as I've sort of indicated here, this M is able to express. And then the other reason I like this is because it's just a lot easier to define a new one. We don't have to worry about like showing the monad laws for these complicated transformations between representables. Instead, we can just say, okay, if we're able to compose operations in the right way, and there are some equations, but they're not as bad, we've sort of reduced this to its essence. It's the simplest combinatorial data. And several authors in the literature, I think, were already sort of implicitly using this when they define certain familial monads. But in order to do things like the enrichment construction that I mentioned earlier, I needed it to be very formal. Like, what is the category of these things? And what do I need to construct a new one that isn't always going to be something that people are familiar enough with to believe something vague? And so this got me, you may not see it coming thus far, but proving this result ended up getting me interested in polynomials. Because if you try to prove this directly, which shouldn't be that bad, right? Like, we have S and E. S and E give us the functor. It's just this functor. And then something, something, E and M give us eta and mu. That's all true. But showing that those constructions, especially for eta and mu, satisfy all the monad laws is incredibly tedious. And so to avoid doing that, at least as much as I could, I upgraded this to something a little bit more categorical, which makes use of polynomials. So this turns out to be a corollary, in fact, of the following theorem, which is that the 2 category, which I'm going to call fan, and is a subcategory of capital cat, of locally small categories and functors and transformations. And this has objects given by these presheaf categories, are morphisms or one cells, are familial functors, and if I haven't said what that means in general, it's functors which look like that, but I'll repeat it again in a moment. And 2 cells are Cartesian transformations. And in particular, in this category, a formal monad, by which I mean a one cell with the same source and target endowed with.
Sorry, so the objects are at category C together with a presheaf? No.
No, so the objects are presheaf categories. This is a subcategory of cat.
Okay, they're presheaf categories.
So yeah, these are presheaf categories.
Okay.
Yeah. And then the one cells are just a particular class of functors, which we know to compose and include the identities. And we restrict to Cartesian transformations. And the formal monads in this 2 category are precisely the familial monads that I'm interested in. And the theorem then is that this is equivalent, or rather biequivalent, to a bicategory I call rep. And I'll tell you what that means. So our objects are small categories, which I'll keep writing as C and D. Our one cells are what I call familial representations. So S is a functor from C op to set, and E is a functor from the category of elements of S now to diagrams over D, because we've changed this to go between different diagram categories. This is called a familial representation. And then I'm not going to tell you what the two cells are for the sake of time. It's not going to contribute anything too meaningful right now. The point is that they are the sort of appropriate Cartesian transformations. And what this result implies is that the formal monads in these two agree. And so on this side, that's familial monads. And on this side, that's these tuples S, E, little e, and M. And so proving this characterization reduces, or maybe reduces is the wrong word, but is implied by proving this by equivalence. But this is hard. And hard for kind of an unexpected reason. The hard part is showing that taking C to C hat and SE to the functor which sends C to again, this disjoint union of representables indexed by these arities coming from E. This is what we want the bifunctor to be. It's not hard to show that if it is a bifunctor, it is an equivalence. What's hard is to show that this is a bifunctor, that it respects composition in an appropriately coherent way, especially given that this is in fact a bicategory, it's not a strict two category.
We should probably wrap up fairly soon.
Okay, great.
40, I think.
Oh yeah, sorry, I lost track. Maybe I'll just say one more thing and then I'll stop. So I'll just get to polynomials as the last thing I say. And so the strategy here is that instead of going from rep directly to fam, we can compare rep instead to a bicategory of what are called polynomials, which I'll briefly explain before I finish. And this is much easier to show that we have a bifunctor into, categories and functors. And this composite is actually going to factor through fam and be an equivalence. So I'll just tell you a little bit about how we compare these things with polynomials. So given a pair S and E, we form a diagram of small categories where we have the category D down here, we have C over here, we have the category of elements of S here, and in this place we have a category which I call GR of E. And we define this GR of E as a Grothendieck construction of the following. We have the category of elements of S. This goes into diagrams over D. Those give us categories by the category of elements. And in fact, those categories lie over D. And so then GR of E is an op fibration over elements in S. We get this diagram here, and these can be used to give functors between categories by taking pullback followed by exponentiation followed by this sum This is where polynomials come in, and we can restrict this to a functor between diagram categories using the fact that C hat is a subcategory of cat over C given by discrete fibrations. So it's a quick summary of how this works. The point of it is that diagrams like this have been very thoroughly studied already, and people have already worked out the coherences of how to go from them into categories. And so in order to prove this statement, it just sufficed to construct a new bicategory of polynomials that suited my needs, had to make it a little bit bigger in some ways, smaller in others, and then show how this construction behaves with composition, which is not strictly preserved, but close enough. And so I'll stop there.
Any questions?
So I have a question. So first of all, this is very cool. Thanks for comments about it. And it's very interesting to me because one of the things that I try to do is build software that lets you represent different categorical structures in hopefully a fairly uniform way. And so one of the things that I've been using are these things called GATs, generalized algebraic theories. But one thing that I don't like about it so much is that it's very syntactical in nature. And so I've been on the lookout for more combinatorial kind of approaches to doing that stuff. So something like this is very appealing from that point of view. And maybe later I'll ask you to tell me more about what little e and little and m are, because I kind of like to see how all the pieces are. So one thing I was wondering though is how, from what I understand, some people have taken an approach to the categorical semantics of GATs or other dependent type theories, where you start with a step that looks similar to the first step of this, where you make a category that's going to describe your types. For the theory of categories, you have of and hom, and you have so exactly that part at least so far is the same. But then, so I'm wondering if you have a sense of how the class of structures that one can get from this system is related to what one can get from GATs or related things like finite limit theories.
Yeah, so I'll admit I don't remember exactly the definition of GATs.
So I think you can also just think about finite limit theories.
Yeah, well, so all of these are finite limit theories.
Okay.
I can offline talk about how, in fact, David and I were just talking about before this talk, how you can go from one of these monads to a category, to a finite limit sketch. So this is what I was hinting at when I first described schema. You can get a finite limit sketch out of this by sort of taking all of these all of these diagrams ET, sort of freely generating the algebraic structure on them, and then taking the category of those algebras. And this gives you, and so the simplex category, for instance, is an example of this. And categories are models for a limit sketch on delta. And you can generalize this completely. You characterize the nerves of the higher categories, and they are precisely then models of a finite limit sketch. In the other direction of like maybe which finite limit theories are of this form, so I can tell you that these are the ones, I'm going to try not to butcher this, I've thought about this before. If you have a finite limit sketch, which is complete in some sense that I don't remember, then these are the ones where your formal limit cones in the sketch are actual limits in the category. So in delta, for instance, the n simplex in delta is a colimit of 0 and 1 simplices, a colimit in delta. And so the limit sketch would be delta up, where the statement for limits would hold. And so I believe that among appropriate limit theories, these are the ones where you actually where it's actually a real limit in the category where you build the sketch.
Interesting. Yeah. So I have kind of a related question then. So like with a general finite limit theory, right? You would have like a category of models and a category of homomorphisms, but there may not be like two cells. Whereas for all these categories, higher categories and stuff, there are higher levels of morphisms. And so does that fall out of this formalism? Like do you get those sort of?
Yeah, so you definitely do. So the category of algebras for one of these monads is, like you said, or equivalently models of a sketch. That's just a one category, but all of these, I believe all of these are Cartesian closed. And so they're going to be self-enriched. So two categories are going to be enriched so the category of two categories is enriched in two categories, and therefore forms a three category. You can automatically form in a certain way. You can automatically form what the appropriate transformations are, and they just kind of fall out from what your cell shapes are.
That's really nice, because that's like a defect of like the GAT approach if you're a category theorist. It's like, oh, where are all those higher level business, right?
Yeah, and this is something I really like about this. I mean, I mentioned at the beginning some sort of like higher level concept, like limits, vibrations, yoneda, that we want to get. But even the basic stuff, like natural transformations when they should exist.
Exactly, that's super nice.
Those do fall out. I remember a few weeks ago somebody suggested that maybe the particular way I was defining them might not be ideal, but there are ways to do it. And so that's something I like about this.
I have two small questions, if I may. I don't know if anyone else is trying to ask questions there. But first one is about fun, because any familial, does that come from the families that one uses for modern independent type theory? Is this to be a source of families? I mean, where does the name familial comes from?
Yeah, so it comes from, familial is short for familially representable, because here we have one of these functors here. It's a disjoint on each component for each cell shape. It looks like a disjoint union of representables, and so you sometimes I called this a familial representation. It's also been called a representing family, which is maybe a little bit more evocative. That's where it comes from. I think I first saw the term used in an appendix of Leinster's book, though I'm pretty sure some other authors were talking about them before then. These are also the same as parametric right adjoints, which I think has become more popular in a lot of settings.
Yeah, I think it has parametric right. PRAs is kind of, at least that's how I have heard about them.
Yeah.
And I think that this other small question was about, I mean, it's a bit of a joke. I wasn't, you started talking about higher cats, so lions and stuff. So can we kind of try to talk about the bike categories as being humans or jaguars or something? Can we try to, no, I mean, it's a joke, but it's not a total joke. Because, I wanted to see if you had in your head some sort of personal description of the different sorts of categorical structure that those higher categories kind of bring to the table.
Well, in a practice,
I want one.
I will say that in a practice version of this talk that I gave, I said something about if we're talking about all of the big, the large breeds of cats in the world, it never hurts to include ordinary house cats, which would be the one categories. I might have been a little bit overly bold when I said that two categories were lions, because we do get bigger and bigger from there. But maybe you could say something like, see, I just don't know if we have enough cats. Do we let maybe lions are N categories? They're kind of the most popular, at least that I know of. Maybe double categories might be more like tigers, where they're similarly powerful, but look a bit different. Not sure how much I wonder what multi-categories would be, because they're still kind of one-dimensional, but then they have all of these different kinds of...
Maybe mountain lions, because they look like kind of smaller things. They pack a punch, but without...
Yeah, that's good.
Doing much.
I saw a movie recently where there was briefly a cat with many different tails. I didn't write down the category of cell shapes for multi-categories because it's actually quite big, since you have an n to 1 arrow for every n, but somehow that image kind of came to mind.
I think anything that we can do to make these things a little bit more familiar or more understandable, kind of, it's useful. Because the structures are kind of, they're complicated, right? There's no tool about it.
Definitely. And one of the reasons why, I don't know why I keep looking at this board. One of the reasons why I was really interested in generalizing these is because new breeds of cats can always show up. You never know what's going to happen in the world that might cause a new kind of cat to come around looking different. And this hopefully will give us some sense of how to properly train them when they arrive. Because even now, people sometimes talk about cubical higher categories, which are relatively untested. I always joke that, most category theorists have invented a new kind of monoidal category, which also fall into this formalism. And even with bicategories, there's multiple different ways of defining them, which you can do most of them in this formalism as well. And so having sort of I'm hoping for there to be more varied types of higher categories used that we could then hopefully describe more easily.
I don't know, probably people have more questions there, but I have another one, if it is very possible, which is the business that you're saying about directed. When you're talking about the enriched categories, you said that the bases had to be directed. I thought for enrichment what you needed was a monoidal closed category on the basis. That's what Kelly says.
Yeah, so I think I was unclear in that. So I'll say something very brief. about that. So what I was saying about directed is sort of a maybe unfortunate level mismatch. So what's something that we know that we want to know how to enrich? We want to be able to enrich, say, double categories. Like that would be reasonable. And this has actually been written about, at least in an unpublished note by Marcelo Aguiar. And the cell shapes here, well, we have our dot, we have our horizontal arrow, we have our vertical arrow, we have our square, and we have sort of source and target maps for each of them, like so. And, oh, sorry, I was tapping the mic. Apologies. And so what I mean by directed is that there's a top dimensional cell, namely the square, which doesn't have any outgoing morphisms. That's what I mean. So, which means that at this particular point, it looks like a direct category in the sense of like all of the morphisms point one way. What we enrich in is actually sort of, I mean, I could give a whole talk on that, but the top line is that the theory of categories, you can canonically extract from it the fact that a category should be enriched in a monoidal category. You can canonically extract that a two category or a double category should be enriched in a braided monoidal category. That's actually not entirely true. You can do better. You can use a duoidal category, and my theory does not recover that without some extra work. But for my favorite one, a multi-category should be enriched in a operad object in cat. So you've got like rather than sets of operations with each arity, you have categories of operations with each arity. And this is the natural thing to enrich a multi-category in. And so you can sort of get one of these for each type of higher category. And sometimes you even get like familiar things anew, where you can actually, so monoids are a type of higher category, where your cell shapes are just points. And you can enrich monoids in any monoidal category. And a monoid enriched in a monoidal category is just a formal monoid in that category. And so you can recover a lot of like other constructions from this general enrichment. But yes, the base has nothing to do with directed. It is something that you have to construct from the theory.
Sounds good. Thank you. I mean, at least I can see where the directedness is coming from on the little diagram.
Yeah.